So we arrived to the last part of this series of very brief talks and music pieces. And the last part is about gravitational waves. So I thought I would show you this figure over here that represents 13.8 billion years of the universe. So I told you before that by measuring the temperature fluctuations and other properties of these fluctuations of these photons that come from the Big Bang, we can learn about the composition of the universe and about the physics of the very early universe, the physics of the very fraction of a tiny fraction of a second after the Big Bang. And to explain a little bit more about that, let me introduce you to a standard paradigm that we have in cosmology today, which is the paradigm of inflation. So in order to explain why the temperature of these photons was so similar in regions that are so distant in the sky, scientists came up with a theory to explain this, and this is known as inflation. So inflation happened, this theory says that it's a period of accelerated expansion right after the Big Bang, at a very fraction of a second after the Big Bang, when the universe was smaller than an atom, and it expanded very rapidly. Now, the space-time had small fluctuations at the time, and with this very rapid expansion, these small fluctuations in the space-time, already predicted by the theory of general relativity, expanded, and under this theory, they expanded and they gave rise to what is known as primordial gravitational waves. So if primordial gravitational waves were to be detected, this would be a smoke gun of the theory of inflation. Now, how do we go after these primordial gravitational waves? It turns out that these primordial gravitational waves leave an imprint in the way these photons, this light, oscillates. This light is polarized, and by polarized I mean it oscillates in preferential planes, and these gravitational waves leave an imprint in this polarization that the light has. So there are telescopes that are already taking data and are being planned for the future that are going after this specific signature in the cosmic microwave background, that it's a type of polarization that would arise from these primordial gravitational waves. What would we learn? We would learn the energy at which this period of inflation happened. And this energy could be very large. This energy could be the largest ever achieved, larger than any experiment that exists or will exist ever on Earth. So this is a window of very high energies in the very early universe. We can use the cosmic microwave background statistics to learn about 10 to the minus 36 seconds after the Big Bang, and learn what kind of physics happened, what was the energy at which this physics was happening. So that's why cosmologists are interested in these primordial gravitational waves. And with that, I will leave you with the musicians for the last part.